everybody. This is Mr. Johnson, and welcome to AP Chemistry. It is requested that people have a chemistry background before taking AP Chemistry, and the point to this particular video is to shore up some particular skills that we might have from chemistry or even physical science. If you find it's going too fast for you on particular topics or you need a little bit more, don't worry, I've got other videos in there, and I am going to talk actually pretty fast through this particular unit just because it's meant to be a review to brush up on some skills. So let's get right into it, and what I'd like to do is start with this particular diagram that goes through a little bit of the background behind what's being communicated within the atom. Now, an atom is a neutral particle that has the same number of protons and electrons, and we'll get into some other things along the way as we get into this further. But when we look at this particular graphic from the periodic table, I see that I've circled the atomic number for carbon. What that atomic number does is it tells me the number of protons that are found within the atom. Okay, the number of protons in an atom will actually reflect also the number of electrons because it's neutral. And from there, we can also take a look at our atomic mass. Okay, so with that particular thing, you'll see I circled the atomic number. Once again, that's the number of protons. When we look at atomic mass or the mass number, that tells me the number of protons and neutrons. Okay, so there's a difference there, and we need to be able to figure out or recognize those things along the way. I can use this graphic then to figure out the number of neutrons. If I see that we have the number of protons already indicated with number, and I see that we have a mass number of 12, if I subtract off the 6 protons, then I would have 6 remaining neutrons. Now, you might see that I have a 0.011 in the atomic mass in there. That's because we take an average atomic mass considering other variants of that particular atom. Okay, so I'll get to that in just a moment. Another thing that I want to emphasize with this is in chemistry, we very rarely talk about just the stable element by itself. We always talk about the ions that are formed from those. So the ions are going to be either positive or negative. And one of the things you have to continually wrap your head around is the fact that electrons are the things that will make the ions. Okay, so electrons, if you lose electrons, which are negatively charged, you'll become a positive ion, what we call a cation. If you gain electrons, you're going to be gaining something negative, so you become more negative. And so that would be a negative charge on there, and those are anions. Okay, now another thing that I had mentioned just previously was that there are different variations of an element out there, and we call that an isotope. Now, you notice in this example, it's lithium every single time. That means that lithium has an atomic number of 3, meaning 3 protons and 3 electrons if it's going to be a stable element. But what's different here is the number of neutrons found within. And so that's why we're finding the atomic mass or the mass number is going to be different. And we do a weighted average of those to figure out the average atomic mass. We just have to know how many of each type of lithium is out there to figure out an average atomic mass. Okay, so that's a pretty simple concept with there. We'll work with that a little bit more later. Another concept that's huge in chemistry is the concept of significant figures. Now, I know students get confused by this at the beginning because we're not used to, in math class, we're not used to actually relying on the validity or the accuracy to what level of detail we've been collecting these numbers. In math class, it's just theoretical, but in chemistry class particularly, not so much as in biology or other fields of science, but in chemistry, we have different ways of measuring. And so our numbers have to tell the reader what level of accuracy we've been reading these numbers to collect our data. So if you take a look at number 1 in the beaker, and I'll talk about these tools later on, but in the beaker in number 1, that's actually just a very, very rough estimate within each of those marks. We have a mark for 20, 40, 60, 80, 100, but those marks are not meant to be all that accurate. So we go down to number 3, those would be down to the 1's place or the 10th place even. And those numbers are going to be highly specific in there. Also remember, when we are measuring things in science, especially chemistry class, we measure those graduations, those markings that are on there, and we bring it 1 decimal level past that. And so then we do our math with this. And so there are rules. When we see numbers being reported in chemistry, there are rules to tell the reader what degree of accuracy have we been measuring things. Okay, so one of the things that we need to just wrap our head around is that the number itself is going to tell us something. So if I see a set of numbers, and let's just say that it's a 123.4, this number that I've recorded down tells the reader that we've got a measuring tool that measures the hundreds place, the tens place, the ones place, and then the last value is what the reader has been estimating along the way. That is a valid number or a significant figure that is of value to our math. But we all understand that that 4 could be interpreted as something else by a different reader. That could be a 5, that could be a 3, could be a 2. There is no steadfast rule with there. But the point behind this first rule is saying that every value that is a non-zero is going to be significant. It is going to be a factor in our math. Okay, so let's go and look at the other problems, and you can see that really the issue is about our zeros. If I see a number that's reported out that has a leading zero in it, that's not considered a significant value. So by that, I mean a leading zero like this. I have 2 zeros right here in the tenths and the hundredths spot. They are not considered significant. And what we mean by that is I could actually get rid of those zeros. I don't report them out if I translate this to scientific notation. Okay, so that's a leading zero, and they are not considered significant in there. So there are, in fact, 3 significant figures in there. If I see a number where the zero is actually trapped, so 1023.4, this zero obviously would be measured in there, and so that is significant. Okay, then we get to the next concept where we have a trailing zero. Now, with that, what we mean, and we're talking about zeros that are going to be after a decimal place. So 12300. Now, really, there is no mathematical difference, I guess, between these two numbers. So the question is, why in the world would we include those zeros? Well, the answer is simple, because somebody took the time to actually measure them. Okay, that tells me that I had a measuring tool that went to the ones, the 10th, 100th, 1000th, and the 10,000th place was actually estimated. That's highly more accurate than something that just went to the ones, 10th, and then somebody estimated the 100th place. Chemistry is very detail oriented, and so we need to pay particular attention to the accuracy of those numbers being reported. Now, there is another thing that we need to keep in mind when we're doing some kind of conversion or a counted object. Say I have 20 students. Well, this zero is not just a placeholder. That is actually a physically counted thing, so that would be significant. Or if I have a conversion factor that says I have 60 seconds in 1 minute, there's actually an infinite number of significant figures in each of these values, because it is without a doubt the same value that everyone is going to be encountering here. Okay, so I mentioned placeholders before, and that was with our leading zeros. There is another time that we see this, and this is a placeholder zero, a set of zeros in here. In other words, I have 1 times 10 to the third, zeros are gone. So those are placeholders, those are not significant either. Okay, so those are just the basic rules behind it that we get used to. And here's the reason we want to ask those questions, is because we have different ways of rounding our answers to reflect the degree of accuracy when we do our math. Most of chemistry ends up being a multiply or divide function. So we're going to round to the least number of significant figures. Okay, our answer needs to reflect that. Now, let's consider something that you see in math class, elementary math class. We multiply 5 times 5, and everybody knows 5 times 5 is 25. But remember, in chemistry class, these are measured things. And so we know that we have not hit the tens mark, and this 5 is actually a very soft 5. That ones place is actually being estimated along the way. And so that could be a 6, it could be a 4, it could be a 3. So this value can't be all that reliable. And we need to round our answer to the least number of significant figures here to tell the reader how the degree of accuracy or confidence we have in our number. So I see 1 significant figure here, 1 significant figure here. So this answer at the end, I still use my calculator, but I see, oh, there's 1 significant figure with a 2. The next number is 5 or greater. And so I call that answer 30. So this zero, remember, is a placeholder zero. He doesn't count. So 5 times 5 is actually 30. And so you might wonder, well, when is 5 times 5 ever 25, like we learn in math class? Well, what if I took 5 times 5.0. We have two different measuring tools here. We have the zeros, the 0 to tens place, and this is a soft 5, but here we have a measuring tool that everybody knows the ones place, and the person estimated the tenths. And so we still have 25 in here. I have one significant figure, two significant figures. I still round to the least number of significant figures, 1. The next number is less than or is greater than 5, so I would round that to 30. But what if we took a measuring tool that we went 5.0 times 5.0? In other words, we have a measuring tool in both cases that everybody knows the ones place, and we're estimating the tenths. Well, I have 25.00, but here I have two significant figures. Here I have two significant figures, 1, 2. The next number is less than 5, and so now I have an answer of 25. So it's all to reflect the degree of accuracy of our measuring tools. And so then we have a different set of rules when we get to adding and subtracting, however. Because of the reliability of those numbers, the softness of those numbers, if you will, if we add together a 3.1 plus a 7.12, if I add that all up, I have a 2, and a 10, okay? So now this is saying that we round to the least accurate decimal level. I don't care that there's two significant figures here and there's 3 here. I don't care about that. What I do is I look to, this is only accurate down to the tenths place. And so there's my tenths place. The next number is less than 5. So my answer will end up being 10.2. Okay, so that's how that works in terms of rounding with significant figures. Now, it is a very valid question. Why do we have to do this headache? The College Board has already said that they will have a set number of questions within the FRQs, or the free response questions, will be looking at your significant figures. They will dock you points if you don't round accordingly. So it's important that way. But the biggest thing is chemistry is a highly detailed subject, going down to the thousandths or 10,000ths, because these things are so light in mass. The slightest change in the decimal level will make a huge difference in our overall products. Okay, so here are some tools of the trade, just so we get used to that and we don't lead into false senses of accuracy here. I've already mentioned number 1 is the beaker. That's more of just a liquid container than it is meant to be a measuring tool. And similar to that is going to be our Erlenmeyer flask. We use the flask a lot of times to, again, hold the liquid, but we use that one more often in lab because it's curved at the top, curved inwards, so any splashing is mitigated, okay? When we want to get down to more accurate measuring, we want to get into the graduated cylinder, or if we get into more specific things, the next 3 sets out there are going to be our go-tos. The volumetric pipette usually has a little marking. Maybe it's, just right around this mark right here or whatever. That's going to tell us how many milliliters to that line. When we get down to the next one, a volumetric flask, a little bit more, there's going to be a line, and down here it will tell you, is that the 25 milliliter line, the 50, the 100, or whatever. What we do is we bring that value to our liquid to that line, and you read the bottom of the meniscus, if you remember. Okay, that will tell us very specifically how much is there. Now, if we want to dispense a certain amount into our beaker or flask, then we use what's called a burette. And so we fill up in number 6, we fill this up, and we can actually dispense down the bottom here a certain amount, and it'll just drain out the bottom, and we can record our starting volume and our ending volume, and we can record how much volume we've dispensed into our containers. Okay, that's just tools of the trade that we'll be working with. Each one of these, don't forget, as we look, we see, this is going to the ones place, so I would read this down to the tenths. If this one has down to the tenths place, I would actually report a value down to the hundredths. Okay, we always read, even in like a meter and things like that, if we're using a ruler, if we're using a thermometer, each one of our values that we record, we bring one past the marking of whatever graduation is there. Okay, now I always use this graphic for the metric system because I did my student teaching down in Australia, and it just kind of brings to mind the concept of kangaroos hopping down the mountain drinking chocolate milk. That's just the kilo, the hecto, the deca. This is our base unit of the meter, or it's going to be the liter, or it's going to be the gram. This is the deci. Notice that's a lowercase d. And here's the centi and milli. This is a base 10 system. And so what I use this graphic for is if I want to take, say for example, 1.0 grams, and I want to know how many centigrams that is. The nice thing about this, if I've got the number right here, here's my decimal point, and I'm in the gram, I just bounce my decimal 1, 2 times. 1, 2 times, and so that becomes 100 centigrams. Okay, so it's a pretty easy system when we go base 10. Now, you do have a reference chart that was handed out the first day, and that will have other conversions along the way. Make sure you use those, because there are other conversions that we'll need to use that go beyond just this base of 7 different conversions here. For example, there's 2 spaces. I forget what the names of those things are, but we go from milli, a couple spaces, then we go down to micro. Then we have a couple spaces, then we go down to nano, and then we go a couple more spaces, we go down to pico. Remember, we're counting very, very almost invisible things. You can see them with an electron microscope, but we're going to get down to the picometers. And similarly, we go bigger and we get mega, and we get up to here, we get giga, and we have tera and all those other things. So chemistry deals with incredibly small and incredibly big numbers. That's why we've got to be confident in our metric system conversions. Okay, now, another topic that's huge is our periodic table orientation. When we get a periodic table, we've got to be sure that we're all using the same terminology along the way. So this is just an example from Concordia's periodic tables. I like this one because it's color-coded for us. But one of the first things you'll see here is to label the periods. There are 7 periods on our periodic table, and those are our rows. Okay, so that will tell us what period or what row number a particular element will belong to. Then we get to our groups and our families. Okay, that's going to be our columns. And there are 18 different groups or families. Those are our columns. And that will tell us our traits. For example, we have our noble gases. If we take a look at some of these other ones in here, we have the halogens, and we have the alkali metals, the alkali earth metals, and so on. Now, you'll see that along the way on this particular periodic table, they're color-coded in yellow, but on most other periodic tables, you're going to see this. You're going to see a staircase, and that's the line that delineates where our metals are versus our nonmetals. Our metals are on the left and underneath the staircase. Our nonmetals are on the right, and with the exception then of hydrogen. Hydrogen's over there in column 1 because it has the same similarity or traits as the rest of those elements in there, but it is a gas, so it's a nonmetal too. But that staircase is going to be our metalloids. Okay, they have properties of both metals and nonmetals. And so I use a down and over rule, starting with boron. That's the first metalloid. We skip aluminum because we know that's a metal, but then we have silicon, then we go down to germanium and over to astatine, down to antimony, over to tellurium, down and over, down and over. Those are the things that will be telling us are metalloids, okay, separating the elements from those. Now, we have some general ionic trends, and here comes that word of ions. Ions are what charge an element might take over. Remember, an element is a stable atom. Number of electrons and protons are the same, but they will tend to take in electrons or give up electrons. And so we have the cations. Remember that those are the things that are positive. And so that's everything that's going to be over on this side. It's going to be an easier system. And I say that hesitatingly because AP Chemistry Board has very strict rules about how they want to phrase things. But if we take a look at something like calcium, it has 20 total electrons, but in period 4, it has only 2 electrons. And we'll get more into that in future chapters. So don't worry if I'm going too fast on this one. The concept is, right now, calcium has 20 total electrons, but in energy level 4, it would like to have a total of 8, okay? But it only has 2 there. So the question is it easier to lose 2 electrons or to gain 6 more to get over to the noble gas area? Well, it's easier mathematically to get rid of 2 electrons. When you lose 2 electrons, you become positively charged. Now, if we take a look at something like oxygen, for example, well, it has only 2 spots to go before it reaches that noble gas column. So it's easier for oxygen to gain 2 electrons than it is to lose 1, 2, 3, 4, 5, and then this one here would be 6. It's easier to gain 2 electrons, so he will become an anion, and that will give it a negative charge. Okay, so that's just the concept behind ions. Okay, now, Another thing that we get, and this is where I was mentioning before, is the reason it will gain or lose those electrons is to become what we call more thermodynamically favorable. In Gen Chem, even in textbooks, it'll always say that we want to reach a full octet to become stable. And they were very clear in the AP board that they will not take that answer. They want you to use the phrase thermodynamically favorable. Okay, it is more stable in concept, but they just kind of do it that way. Now, what ionic compounds will do is they will simply give up or take in electrons, like I've been describing. Okay, the concept is we will swap, drop, and reduce those charges. A cation, like I said, will lose electrons. Anions will gain those electrons in and become a negative charge. And so what we want to do is make a compound that's overall neutral. So let's take a look at this example of lithium sulfide. Lithium is in column 1, which means that it will form a +1 ion. Sulfur is in column 16, which means it will form a -2 ion. Now, I say swap, drop, and reduce. I could simply just go like this, and that's how I get my Li2S. But if we look at it mathematically, if I'm going to form a stable compound between these two, and by that I should say neutral compound, I would need 2 lithiums for every 1 sulfur. 2 times +1 is +2. 1 times -2 is a -2. So +2 plus a -2 equals an overall charge of 0. That's what we mean by thermodynamically favorable, is to make it so that it's overall neutral. Okay, so it's simpler to just see it swap, drop, reduce, but in concept we're seeing a 2-to-1 ratio. So let's take a look at an example of, let's say, calcium sulfide. Okay, and why I say swap, drop, and reduce. Well, if I had calcium sulfide, then you'll see the 2 will go over here, the 2 will go over here. You would think that we'd have Ca2S2. But in fact, I only need one of these and one of these to become neutral, or to become a 0 charge. And so I would do a swap, drop, and reduce to become CaS. Okay, so when we have just 2 elements involved, that's what we call a binary compound of a metal, and that's going to be ionic. And so we would just simply write it out that way based on charges. And notice that all binary compounds of the ionic nature start with the element name, and they all end in "ide." Now, if we have other ones, we do have an exception on there that we want to make sure we're aware of, is that column of our what we call the transition metals. That's columns 3 through 12, kind of that sunken down region of your periodic table. In Gen Chem, I have people memorize just certain elements, because we work with those all the time, that would have different oxidation states or different charges in there. But in AP Chemistry, every single transition metal, because there's so many variations out there, will need a Roman numeral in there. And that's where this comes in. That Roman numeral tells me the charge of that particular element, okay, that particular ion. So that Roman numeral 2 means that the charge on the iron was a 2. Chlorine is in column 17, meaning that it'll only need to take in one particular electron. So we're going to take the 2 here, the 1 here, and that's how I get FeCl2. Okay, so just watch out for your Roman numerals along the way. They mean the charge. Now, the next thing that we need to take a look at are ternary ionic compounds. Ternary means we have more than 2 elements in there, 3 or more, and so that's where polyatomic ions come in. You do have a listing of polyatomic ions on your reference sheet, but I would strongly recommend you guys get to work on memorizing those. So phosphate, when I see phosphate, I need to see a group of elements already formed together with an overall charge, okay? That's PO4 with a -3 charge. And we're going to mix that in this example with calcium. And so calcium, I already said, was a 2. So the 2, I will need 2 phosphates for every 3 calciums. It becomes Ca parentheses PO4 and 2. So Ca3 parentheses PO4 parentheses 2. 2 phosphates are needed for every 3 calciums. Okay, so that group, that polyatomic, sticks together as one grouping in there. And then we get to the other lovely exception of our acids. There's a couple different examples of acids out there that we need to be aware of. Acids you can identify because they start with hydrogen. The only exception to that, chemistry is full of exceptions, is going to be acetic acid. That one ends with hydrogen. We'll talk about that one later on in class. But what I want you to see here is that for the most part, acids start with the element of hydrogen and they follow a very set naming system. If there's only two elements in there, we know the first one is going to be hydrogen. If there's only two elements, it's going to follow this particular naming template. We just pop the second element's name in that blank. We call this hydroic acids. Hydro just means that it's going to be hydro something ic means it's going to start with hydrogen, and so the other element is going to be chlorine. We just look at charges. We could have a hydrosulfuric acid. So hydroic means that it's hydrogen plus something, and that's going to be sulfur. Sulfur has a -2 charge, and so I'd have H2S if it was hydrosulfuric, and so on. Now, we also have ternary acids. Now, ternary acids means that I'm going to have my polyatomics once again. So it starts with hydrogen, and the question is, which polyatomic are we going to have? So if it's an ic acid with that particular acid, that means it's some kind of hydrogen with some kind of 8 of our polyatomic ions. If it's an us acid, it's an ite polyatomic. So here is the example of sulfuric acid. Okay, sulfuric acid means that I have hydrogen in front and it's sulfate, which is SO4 -2. If it's sulfurous acid, then it's hydrogen with sulfite, which is SO3 with a -2. Okay, so that's just how naming of acids work and why those symbols fall in line like they are. Okay, acids does take a while to get used to. This is meant to be just a quick review, and you can go more in depth later on as we go. Now, going back to this concept of forming bonds and everything, I've described this entire time forming metal bonds, okay, ionic bonds, where we give up electrons or take them in. There is an example when we are sharing electrons back and forth, and those are with nonmetals. So that's what we call a covalent bond. And so in those types of examples, they're not giving up electrons or taking in, they're sharing them back and forth very actively. And so we have prefixes that will tell us how many of each element is there. That's not going to be in terms of charges at all. So if we have some examples like this one, we would call this nitrogen trihydride. Common name would be ammonia, but nitrogen because there's only one, and then we have 3 hydrogens in there, so that's why we have trihydride. Now, we can also tell other things within this. With our covalent bonds, we have polar bonds, we have nonpolar bonds, and that has to do with electronegativities. So for that, we would need to see some charts, or we need to be able to draw it out. And so that's one of the concepts that we'll get into in AP chemistry. But one of the simplest ways to do it is just when we're given electronegativity charts. That's what we're going to see in our very first unit here is some periodic trends and so on. We can just see some values of things along the way. So electronegativity in the simplest form or definition is for an element or any particular atom to attract electrons, how much it would prefer to take in electrons. Well, as you see, if you go further to the right on the periodic table, they tend to bring in more active electrons. If you go to the left, not so much. As we go up the periodic table, okay, if we're focusing just in column 7A here, the numbers get bigger as you go up, meaning that fluorine tends to take in electrons a lot more actively than something like iodine or astatine. Okay. Now, if we take a look at the differences between those, then we'd be looking at polarities, and a large difference between them would be more highly polar. And if there less difference between those, then we'd be nonpolar, meaning there's no dipole moments. And if you look comparing the nitrogen with the hydrogen in there, if we look at some values, we see within this first one, we see that nitrogen has a value of 3, and my hydrogen has a value of 2.1. Well, the difference is only 0.9. Okay, so that's not going to be very polar. But if we take a look at the difference between hydrogen and oxygen, in the water example, I have 3.5, and we have a 2.1 again. Oh, so my difference is going to be a 1.4. That's going to be a larger difference in there, so that's going to be more likely to be polar, okay? So that's just the concept behind it. Simple math. We'll get into mapping this stuff out in more depth later on. I take a look at carbon tetrachloride, and so just quite quickly we see the difference of 2.5 minus a 3. Oh, it's only a 0.5 difference. That's not going to be very polar in there. Okay, so it's just taking a look at those things for polarities, seeing how distributed out the electrons are going to be. It's not heavy on one side or light on another when in terms of electrons. So polar or nonpolar, that's all we're looking at. Okay, now this leads up to your assignment. All of the sheets that I'm going to be handing out throughout the entire year will be on paper, but I do have a PDF of them for your reference as well. This particular assignment, I do want you to submit your answers online in that red mark where it says the answer form for it. Okay, so this is a long-standing assignment. You have multiple days to be working on it, but what topics are in there is going to be what I covered today. Taking a look at figuring out atomic structures, significant figures, and how to round with the math, doing some metric system conversions, even the math dimensional analysis, that technique we use, is modeled in the second video that I have for you, how to use that technique, because in College Board, just having an answer in the end is not worth anything. You've got to have the work supporting it. Periodic table trends, and also some basics with naming compounds and writing and naming them. That's all included in this particular packet. So this is just a heads up. It's not meant to be done in one sitting. It's not meant to be just throw you to the wolves and good luck with that. You're going to have to do some independent review. This particular video is meant, like I said several times, it's fast. It was just meant to be a quick hitter to practice up some of those things. I have much slower and more detailed supporting videos for you along the way. Feel free, please go back to review those as well. So I don't want to make anyone nervous with this assignment, but there are some expectations that we get up to speed with those along the way. So with that, I wish you guys well, and we'll see you on the next video with that. And good luck. Welcome to AP Chemistry.